All right, my friends, welcome to Calculus Social Distancing Edition. We're going to be looking at section 3.8 on implicit differentiation today. This will be our last technique of differentiation before we move on to all the applications of derivatives in chapter 4. All right, an implicit differentiation is going to allow us to find the derivative of a curve whose equation is not a function. All right, so to kind of show you how this works, I picked probably one of the simpler non-function equations we can have. X squared plus y squared equals a number, gives us the equation of a circle. If I were to go over into Desmos and graph this, it would give me a circle of radius 5, like it would go out to 5. And let's say we wanted to find a tangent line to that function about right there. Of course, Desmos would make that look like a circle and a line, but you can use your imagination. All right, so this equation actually is a simpler one, and it's one that we could actually find the derivative of with the techniques that we know. So I'm going to do that first, and then I'll show you the technique of implicit differentiation and how they give us the same result. All right, so if I wanted to find the derivative of this equation, then I would need to solve for y. Everything that we know about derivatives, we have to have the equation solved for y. So I'm going to start by subtracting x squared from both sides, and that would give me y squared equals 25 minus x squared. All right, and then we would have to take the square root of both sides to solve for y. All right, and that would give me y equals plus or minus the square root of 25 minus x squared. All right, and once we get that plus or minus, we can see, first of all, why this is not a function. If I plug in a value here for x, all right, then this function is going to give me two answers. This equation is going to give me two answers. It's going to give me a positive answer, and it's going to give me a negative answer. So I get two answers for every x. And they kind of make sense from the graph. The positive answer that you get is all these y coordinates on top of the circle, and the negative answer is all these y coordinates on the bottom of the circle. All right, so since I drew my tangent line on the top half, I'm going to keep that positive square root, and we're going to treat this like the function y equals square root 25 minus x squared. All right, so this is exactly like something you did in your homework on the chain rule. You've got an outside function that's the square root, and we rewrite that as 25 minus x squared to the 1/2. And then that 25 minus x squared is our inside function. All right, so I'm going to find the derivative of this using the chain rule. Okay, so chain rule tells me that I'm going to take the derivative of that outside function first by bringing that 1/2 down with the power rule. All right, so y prime will bring down that 1/2. So we're taking the derivative of that outside function, subtract 1 from the exponent. 1/2 minus 1 gives me negative 1/2. Chain rule says to leave the inside function alone, and then to multiply that by the derivative of the inside function. And the derivative of 25 minus x squared is negative 2x. All right, so I can simplify this a little, and I want to so that we'll see something important later. So because of this multiplication, I can simplify this 1/2 with the 2. 1/2 times 2 will cancel out. And then I can also take this thing right here. It's got a negative exponent. I'm going to move it into the denominator with a positive exponent. All right, so y prime, the only thing I'm going to have left up top is from that far right side of parentheses a negative x, and then I'm going to move this 25 minus x squared to the 1/2 down with a positive 1/2 exponent, and then I can rewrite that as negative x over the square root of 25 minus x squared. All right, so that's my derivative of at least the top half of that circle. All right, so now I want to show you how we can find this derivative using our technique of implicit differentiation. So I'm going to do this on the same slide. I'm going to make a divider here so we can compare our answers when we're done. Okay, so implicit differentiation requires us to remember that this y is a function of x. All right, so we're going to treat x squared and y squared in this equation very differently. We're going to remember that y is a function, so y squared is going to be treated like a chain rule where y is the inside function and the square is the outside function. But the x is the regular old variable. Its derivative is going to be as normal. So I'm going to rewrite this equation, and I'm going to say x squared plus y squared, and I'm going to write the y in purple so that I remember to treat it like an inside function. All right, and then with implicit differentiation, instead of solving for y, we just take the derivative of both sides of the equation. All right, so I'm going to take the derivative of everything on the left and everything on the right. Now, on the right, derivative of 25, that's still going to be 0. If it doesn't have a y involved with it, then its derivative is going to be just as usual. All right, on the left-hand side, I'm going to take the derivative of x squared, which is just going to be 2x. And then I'm going to take the derivative of y squared. And just like when I used the chain rule on the left side of the paper with the green arrow, I'm going to do the same thing here. We're going to take the derivative of the outside function, leaving the inside function alone. Okay, so there's the derivative of the square part, leaving the inside function alone, and then I'm going to multiply by the derivative of the inside function, and the inside function is that y, so its derivative is y prime. All right, and that is a direct result of the chain rule. All right, and then I'm going to just write that without so much pomp and circumstance here. And what we're really trying to find is the derivative, so we're just going to solve for y prime in that equation. Okay, so I'm going to subtract 2x from both sides. So I get 2y, y prime equals negative 2x. Then I'm going to divide both sides by 2y. And then y prime, these guys will cancel. On the right, we'll get the 2's to cancel. And y prime is negative x over y. All right, and this is going to be typical with implicit differentiation that we're going to have x's and y's in our answer. All right, so this is our answer for y prime, which looks sort of different than what we got over on the left, but I'm going to show you it's really the same thing. Okay, so over here in our answer on the right, I've got a negative x on top, and I've got the same thing over here, negative x on top on the left. And on the bottom, I have a y, which doesn't look the same here, except if we remember when we solved for y, that's exactly what we got, square root of 25 minus x squared. Okay, so it gives us essentially the same answer. All right, so I'm going to end this video here, and then I will have another one that's got a couple of examples so we can get used to this technique of differentiation. We're going to get to integration later. All right, so see you in the next video.